Okay, hello everyone, and welcome to the first hottest of the 2020 fall season. And the topic of today's hottest is the initiality conjecture, which could not be more fitting for the initial hottest of the season. Now, if you watch this video closely, you may realize that it doesn't quite match up with its ending in terms of what people are wearing and what's behind them. And that's because we had a little mess up when we were originally recording it. And so we are now reshooting the first part of the talk. So this is, if you have any memory of what happened during the first 15 minutes and if what's about to happen doesn't quite match it, we apologize. It's the organizer's fault. But we appreciate the speaker's time and the fact that Peter is willing to reshoot this and make up for our mistakes. So I think with no further ado, I'm going to introduce our speaker today. And there are actually two of them. This is the first hottest with that property. So the speakers are Guillaume Brunerie and Peter Lumsdaine, both of Stockholm University, and they will speak about the initiality for Martin-Löf type theory. Peter will start. So Peter, the stage and the moment are all yours.
Thank you very much, Chris. So yes, firstly, as ever, thanks very much indeed to Chris and Dan as the organizers of the hottest seminar for putting this together, giving the chance of a very nice, very long-running, they were doing Zoom seminars before it was cool, a long-running and very well-organized seminar series, and especially thank you for the opportunity to re-record the first 10 minutes so that I can fix everything I said wrong the first time. But yes, so today, this is a piece of joint work with me, Guillaume Brunerie, Manu Dubot, and Anders Mortbeck as well. We'll get into the sort of division of labor between it as the talk goes on. We'll be talking about the initiality conjecture, theorem, property, whatever you want to call it, for Martin-Löf type theory. So what do we mean by initiality for Martin-Löf type theory or any type theory? We mean a statement of the kind that's very standard in categorical logic, saying that the syntactic category of your logical theory, so let's say dependent type theory with sigma types, pi types, whatever else you want, it forms the initial structure in some category of algebraic structures. The initial contextual category with sigma structure, pi structure, and identity type structure, or whatever else you want. And this is a template for a family of statements that one can have for different theories. When we look at this statement, what is the context for it? The motivation mainly is that it justifies the definition that, if you're a kind of categorical logician you like a lot, of saying that by a model of some kind of type theory, we just mean a contextual category with the appropriate extra structure on it. And this is useful because if you try to directly model your type theory, give an interpretation from the syntax into some semantic setting, there's a lot of bureaucracy one has to deal with. This theorem packages that bureaucracy up once and for all. It tells you that if you've got your semantic setting where you want to model the syntax and you've organized it into a contextual category with sigma and pi structure and so on, you automatically get the unique morphism from the initial one into it, which is the interpretation function from the syntax. And this is a theorem it's a very robust form of it, and we believe that it's a kind of statement that we think should hold for all reasonable type theories, whatever that may mean. That there are some kind of fragile properties of type theories which are important, but only hold for certain theories and not others, like normalization or something. This is a theorem, this initiality, which we expect to hold really for any reasonable kind of type theory we can write down. And there are a lot of slightly different ways as well that we can look at this statement. One can state it with several different, for instance, algebraic structures, category with attributes, category with families, contextual categories, C-systems, and so on. Also, similarly, you can use various different presentations of the syntax of type theory. There's a lot of variations we can spin on this statement. As we get on, I'll get onto the specifics, but the first few minutes of the talk will be about all sorts of general theorems along this template. And so I've been calling it a theorem, and there's a lot of times and a lot of people when we would have called it a theorem. And this was, I think, the consensus when I was first learning this stuff in grad school 10, 15 years ago, which is that this statement, the syntax with categories with attributes were first introduced by Martin-Löf, and he gave it, I should have mentioned him on the slides. Martin-Löf gave this for very simple algebraic theories, not yet with the full binding operators of type theory. Streicher gave the first careful proof for a more substantial sort of type theory for the calculus of constructions in his book in 1991. Martin Hofmann extended that proof and refined it in several ways for a somewhat different and slightly larger dependent type theory. And their proof, especially as refined by Hofmann, extends straightforwardly and robustly to other type theories that you can write down. You add more constructors, you add univalent universes, higher inductive types, all those sorts of things, and initiality holds for those along the same lines. I'm focusing on the Hofmann and Streicher, by the way, over other presentations because, well, there are other proofs of initiality out there. The Streicher-Hofmann approach is the one that seems to really extend robustly more than any other approaches I know. So that was how I learned about it and what I would have said in sort of 2008. That's how initiality is proven. Around a little after that, around 2009, various people started to raise questions as to whether we should really see it as established or whether really it was an open problem. And Voevodsky was the person who most notably brought it to people's attention and argued for this. That it's been proven by Streicher and Hofmann for certain specific type theories with a few constructors, but the type theories that we want to know that it holds for have lots more things, lots more kinds of inductive types, maybe higher inductive types, all sorts of extra imaginative type constructors that type theorists come up with. And it's not really so straightforward to extend it, the proof from these small ones to these big ones. It's like saying the theorem's been proven for n equals 3, it extends straightforwardly to n equals 17 along the same lines, which, is it? Maybe it is, but if it is, we should just prove it for n equals 17. We shouldn't say, I don't want to prove it because it's straightforward, why would you need to prove it? We should prove it, we're mathematicians. And also, indeed, it's not so much like n equals 17, but n equals maybe 5i, that we haven't said what kind of cases it should hold for, what kind of type theories. Does it hold for all type theories? Lots of people would say yes, and maybe it does, for a sense of type theory that kind of, the experts, the people experienced in the field know how to recognize what kinds of type theory you can call reasonable, and it holds for those. But you can write down things that one might think were a type theory, one might reasonably argue were a type theory, and that then the insider in the field will say, oh, no, but you can't put that in your type theory. Of course the theorem won't hold for that. That's not a reasonable type theory. So, for instance, if you write down multiple different formation rules for the same constructor or something would give the kind of thing that isn't reasonable. And so the synthesis of these two viewpoints that I feel one can reasonably come around to, initiality is certainly heuristically well understood and has been since Streicher. Since Streicher and Hofmann's proof and so on, since the 90s. The people who know those proofs well, people who've read those carefully and thought about them, do understand pretty well what kind of type theories you can extend it to and how you would extend the proof. But no one's really carefully written down and expressed that understanding. Certainly not rigorously, no one's really precisely stated and proved it, but not even terribly well heuristically. And so it's very hard, especially, either for someone, so certainly for someone coming into the field to figure out what's going on. And even in the field, I think one gets disagreements of what it should hold for. And once one does have that heuristic understanding or come to one's own version of it, the extension of the proof of Hofmann's refinement of Streicher's proof is, in some sense, yes, it's pretty straightforward, that it needs some tweaks, some in the extension, but there's no substantial ideas needed that aren't there in the Hofmann one already. But at the same time, to be sure that it does extend straightforwardly isn't itself that straightforward. That once you've thought through how a lot of details go and written out some tricky cases to check. You can convince yourself the extension is straightforward and didn't involve any new ideas. But there's a lot to check in order to see that. So perhaps one can say it's straightforward, but it's not obviously straightforward by any means. And so what should we do about this? And so the long-term solution, of course, would be that there should be one theorem here. If you've proved the case n equals 1, n equals 2, you don't want to then just prove the case n equals 15, n equals 17. You want to prove the theorem for all n. And here the difficult bit is stating it for all n, is stating the general version. So it would be nice to rigorously define what kind of class it holds, of theories it holds for, what even theories means in this context. And so that's partly answering the question again. And this is something which, since in the last few years, there have been several different quite good proposals for, and I talked about this at significant length in my previous hottest in June, which, here's the video link. So you can all go and watch the video for that now, and I'll come back when you've had a chance to see that. But no, so that's the long-term solution that we should have, would be to just state and prove it once and for all in generality. But that's tricky in various ways. And so as a shorter term solution also, those of us who are saying it is heuristically straightforward, we should just damn well prove it for some specific theory, show that, demonstrate that kind of, show the straightforwardness or the sense in which it's straightforward by proving it for some more non-trivial theories of interest. If it is straightforward, either so straightforward it doesn't need to be proved, or straightforward enough that the ideas are all there, it shouldn't be too much work to prove it. We should just prove it. But again, show for theories that include more of the non-trivial stuff of interest than the fairly small, still fairly toy versions that Streicher and Hoffman wrote it up for. There's an objection here that I want to anticipate a bit, which this is a talk where one needs to forestall a lot of objections that there always are that come up. I'll say a little bit about them here, and then I will ask people with these objections to at least leave them to the discussion, and maybe leave them until, mostly until after any more specific mathematical discussion about the proofs of formalization has happened, because they have a tendency to derail things and get long. But right, so the question is, part of what makes this theorem sort of specific and tricky is that it's about a specific choice of what the semantics are and a specific choice of what the syntax is. And if you make other choices of those, then it gets easier. So I'll address that for kind of, the answer to that is different depending on what syntax and semantics someone is saying they would prefer. I'll address it for a kind of couple of representative examples. But the first bit of the answer to that is, no, it's not so dreadfully hard and bureaucratic that, on the one hand, one's having to make the argument, it's not so easy that it doesn't need to be proved. But at the same time, that's the normal state of mathematics. Kind of, one ends up making the case that it's hard to forestall the objection that it's too easy. But like lots of things in mathematics, I would argue at least, it's not so trivial that it doesn't need to be proved, but it's also not so hard that we shouldn't prove it at all. It's in the sort of normal state. It's somewhat hard, but somewhat tractable. So it's great. The argument that this syntax makes it so hard, make it easier. This syntax doesn't make it so hard, it just makes it a normal amount of difficulty. But there are other syntaxes which make it cleaner and easier, like off-the-shelf essential algebraic syntax. Essentially algebraic theories, they're a nice class of theories, especially popular among categorical logicians, and they give you an off-the-shelf syntax, which we know is immediately is initial for categories with attributes or categories with families or whatever, because those are essentially algebraic theories, at least if you view them one categorically. The trouble with this syntax, and all of this is, when I say the trouble with, I don't mean it means that it's bad to work with it. I mean motivations for working with this and not just with that. Is that essentially algebraic syntax, it's a very general thing. It doesn't reflect the specific structure of the presentations of type theories that we are thinking of being there and expecting to be there when we're working with a type theory, and that is involved in stating and proving a lot of other interesting theorems about type theories. That if you view a type theory just as another essentially algebraic theory without remembering some of its extra structure, you're throwing away a lot of extra structure and you're losing the ability to say some of the things that you want to say about it. And the other major kind of direction of syntax is that some people, many people, including me, like, and that some people prefer to work with and think obsoletes this syntax, which is where I part company with them, are logical framework presentations, where that differs from what I'll call the kind of naive presentation is a syntax where when you have a constructor like pi types, dependent products that look like they're a binder, they really are a binder in what I'll call the naive presentation. In the logical framework, you simplify the treatment of binders a lot by giving a type theory that has, roughly speaking, some sort of internalized dependent product kind of constructor, which lets you abstract your binders out. And so this avoids needing to handle binders for any of the specific constructors of the theory. Other theories are then presented within the logical framework in a way that's cleaner and easier, and there's less new work to do for the individual theories. This, again, part of my motivation for having preferred the naive syntax is that I couldn't, that from the work in the logical framework tradition, some of the other motivating meta-theorems I care about, I didn't know how to do those in a logical framework approach. That is no longer a valid objection because Taichi Uemura has this very nice general syntax in a logical framework approach that makes some things, at least for me, clearer than previous logical framework-based approaches has, and I now feel that reason for preferring the naive syntax to me is gone now, that one can do the other things I care about in the logical framework approach. So, but on the other hand, a reason for still wanting to care about initiality for the naive syntax, and a reason for not, I think, just thinking of naive syntax as sort of something like unpassed strings of symbols or something, is that one wants to, if one has any kind of surface syntax and then a nicer, more structural syntax, one wants them to be linked. If one has, say, passing strings of symbols into any kind of structural syntax, there one wants to do that on the syntactic side. But to link the naive syntax of type theory and the logical framework syntaxes, so this is adequacy theorems, the clearest proofs of those I know, which are the proof given by Hoffman, is my favorite version of it, they are done categorically using initiality for the naive syntax or something like that. So the naive syntax, I feel, is something that one wants a categorical understanding of. It's not so much a surface syntax that one shouldn't directly try and connect it to the algebraic semantics. So, right, so those, I don't want to spend more time on that direction, but I want to at least address a bit in advance why there are the other ways of doing it well, other ways of presenting type theories that make this theorem easier, but there are reasons why I think it's worthwhile having the theorem for this syntax. So the goal here is to prove initiality, and the goal in particular of the project that Guillaume and I and Anders and Menno worked on is to give formalizations, formal proofs of initiality for some specific type theory, ideally something big enough to be approaching book hot. And what we have is two parallel formal developments that were kind of mathematically planned together at the start and then have been formalized in parallel, one by Guillaume and Menno in Agda, and one by me and Anders in Koch. Starting at first, for both of them, and originally with a very minimal type theory for the sake of getting the structure of it set up, but in mind with the key design criterion that everything we do had to be done in a way that we would strongly be confident should extend to adding arbitrary, whatever that may mean, constructors or rules to the type theory. And having it formalized means that anyone, if they want, can test the robustness and the extensibility by forking the formalization and trying to add their favorite extra logical constructors. So this arose sort of within discussions after a logic seminar here in Stockholm, in the before times when you had seminars with a group of people in a room, where we were just chatting about this afterwards and saying it was frustrating that kind of it hadn't been done yet. And kind of I said, damn it, we should be able to just sit down and do this. It shouldn't be so hard. We've got several formalizers in this room, reasonably experienced. We should just be able to sit down together and do it within a week. And we nearly did. Okay, not quite a week, but the Agda formalization by Guillaume and Menot had initiality for this small toy type theory within a month. And then since then, it's been gone on and extended to bigger type theories. The Coq formalization, unfortunately, we can't say the same for reasons which we'll see a bit as I go into the details of this one. So, so that's the kind of outline of the story of where this formalization came from, where it was motivated by. And for the rest of the talk, I'll give a kind of whistle-stop tour through the mathematical outline of the proof, emphasizing certain key points of it, and then a very quick look at the Coq formalization, and then I'll hand over to Guillaume for their side and the Agda formalization. So the proof, as Anders and I took it, uses categories with families, or essentially equivalently categories with attributes, which we'll define in a few slides. But to start with, I would allow how we're setting up the type theory under consideration, being a little bit explicit about what the syntax is. That the syntax we're taking as, there's a raw syntax with binding. It uses de Bruijn indices. It's well-scoped syntax, and it's fully annotated with all arguments, in that raw expressions of the syntax, they're an inductive family of inductive families of sets, type expressions and term expressions, and they're indexed over the scope, the number of variables that can occur. And they're inductively generated by just variables and then constructors. So you have pi types, which take two type arguments and bind one variable in the second. Rats, I'm not getting a terribly useful pointer. Oh, so we have type argument, so pi types, the variable binding of them is expressed by this n+1 in the middle of the slide, that the second argument of a dependent product has one more variable in its scope than the first, and terms similarly. And so they're an inductive family that you can prove things by structural induction over them. And all of the basic lemmas and operations are proven, defined recursively, and the lemmas proven by structural induction over those. Raw contexts are then just suitable sequences of type expressions. Judgments are just suitable tuples of expressions. And derivability is an inductively defined relation on judgments by the usual rules, the structural rules and the logical rules plus the congruence rules for the specific constructors. One small note here, the one way in which this is a bit unconventional. So in most ways, as I've been saying, sort of the naive syntax, we've tried to stick as closely as possible to the simplest way of taking a traditional presentation of type theory as you might find it in any book or paper on the subject, and reading it in the simplest possible, most naive way of what is happening, what is meant by a rule or a piece of syntax or something. The one slightly unconventional thing is that we don't use context or context equality judgments, neither as a primitive judgment form, nor anywhere in the rules, that all of the rules, they just check sort of the type and term judgments. And so the rules can be applied over ill-formed contexts, which is not so conventional, but one can show that that doesn't change the derivability relation compared to the traditional presentation. So it doesn't change things significantly. Right, so that's the syntactic side of the initiality connection we're trying to make. The semantic side will be based on categories with families. So I won't give a full definition, but the key parts for seeing how we're aiming to interpret things are that you've got a category whose objects we want to think of as contexts. On that category, you've got a presheaf whose elements we want to think of as types over those contexts, and another presheaf over the category of elements of the first presheaf. So in other words, that's giving us a set of terms of a given type in a given context, which reindexes suitably under maps of contexts together with reindexing of the types. And then there are various operations and properties, which I won't give the details of, that the key bits we'll need to talk about are simply that you have contexts, types, and terms, and reindexing and so on for them. Some very closely equivalent categorical structures for type theory are categories of attributes or split type theories and those kind of things. And then in order to interpret our syntax into a CWF, I should have said, we should have operations corresponding to the specific constructors and rules of the type theory. So an operation corresponding to the pi-type formation rule, an operation corresponding to the application rule, and an axiom corresponding to the beta reduction rule, and so on. So given this, there's one more concept that we want to define before saying how we'll give the interpretation functions. And this is, I think, our biggest departure from both from the Agda formalization and from Hoffman's version of the proof, which is the notion of using a notion of environments that for a scope n, thought of as a context of length n, but without yet knowing what its syntactic types are, an environment for that scope is an object and a partial, or it could be total, map giving you for each I from 1 up to n a type over that semantic context and a term of that type. And the idea here is that if our object was the interpretation of some syntactic context, then we'd have the n many types of that syntactic context would have their interpretations, and we'd have the variables of those from the context also available as terms in those types. And the idea is that this is exactly as much of the interpretation of a context as we need in order to interpret types and terms over that context. And so now this is what we'll use to define the partial interpretation function, that given a category with families C together with logical structure, so I should say for all of the next few slides, C is a category with families with a suitable logical structure. And if you've got an environment for scope n, so you've got these types and terms, and you've got an expression in scope n, could be a term expression or could be a type expression, then you can try to interpret that expression in that scope. And we'll call that the partial interpretation function. It gives us, if it works when you try, if it's defined, then it gives us either a type in that over that object, according to the pre-sheaf of types of the CWF, or a term in the pre-sheaf of terms. So it's a partial function defined on expressions, given a sort of environment as background, and giving us suitably either a type or term, depending on what kind of expression it was. And this is defined by structural recursion on E, completely by structural recursion. So it may fail because the expressions are raw syntax, they're not yet type checked or anything, but it's something we can try to do purely by structural recursion on the expression. And then we have a few useful lemmas that we want to know about it, that it's stable, for instance, under reindexing of environments, meaning a purely semantic thing. If you've got a map in the CWF and you pull the structure back along the map, then the interpretation here is the pullback of the interpretation here. And this proof is by structural induction on the expression, directly by structural induction on the expression. Lemma that you can also have that the partial interpretation, it interprets a syntactic substitution as semantic substitution. In other words, you've got a substitution you want to do in the syntax. You could either do the substitution and then try to interpret that, or you could interpret the things you're substituting in and interpret the thing within open variables, and then on the semantic side, plug the interpretations of these into the interpretations of there, which comes out as a certain pullback, and those will agree appropriately. And the proof of this is directly by structural induction on the expression that you're substituting into. And then you can show the key thing that one wants that the interpretation, it's partial on syntax in general, on the full raw syntax, but it's total on derivable judgments. And this is structural induction, not on the expression this time, but on the derivation. And then we can also similarly have that, get that partial interpretation is functorial in maps of categories of families, not just on strict maps even, but in weak maps, which is a useful subtlety, though I won't go into it. And this again is directly structural induction on the expression. And so now we can put it together at last into initiality, that the syntactic category of a type theory, it's a CWF constructed by taking the syntax modulo judgmental equality, fits into a CWF with a logical structure, and initiality is now the syntactic category of families is initial among CWFs with logical structure. And these are just putting together the lemmas we had before. The interpretation function forms the functions of the maps. So the existence path initiality is, we have the interpretation function, it's total, and that fits together to give the components of the map on the syntactic CWF. And the uniqueness, on the other hand, follows essentially by the main work of it is done by the functoriality of the interpretation. That this is roughly that functoriality of the interpretation gives naturality of the maps out of the thing, and if you've got a natural family of maps out of an object in a category, you don't need to do much more work to show that the object is initial. And the things I want to, so this concludes the high-level sketch of the proof of initiality, and the two things I want to emphasize as this are that absolutely all the inductions were structural. This is why I gave all of these sort of empty proofs, because they're not empty. The fact that they're all structural is the key thing that makes it extend robustly to other type theories. If you add one more syntactic constructor or rule to the type theory, you get one more case in all your inductions. And the other thing that, for the sake of not eating too much into Guillaume's time, I won't go into is there's no use of equality on objects, but it's nice and it has some practical uses. It's why things work well with weak maps, not just strict maps. But that was why we used environments and avoided context judgments. And so now I'll give a very quick tour. Guillaume, I'll hand over to you. I'll try by 10 past. Very quick overview of the Koch formalization. So it was based partly on a previous formalization that I'd done in collaboration with Erik Palmgren and Håkon Jutterud, which ran into trouble, ran into mud because of several bad design choices. Named variables, just a bad idea. Setoids, which leave you ending up in setoid hell. And instead of starting with a toy type theory, we started with a slightly overambitious one. This time round, we improved a lot of things. And so the good news about this improved version was that several things went very well. Giving the interpretation function, both the partial function and the totality, went very smoothly indeed. The lemmas about the syntax that we used, like admissibility of substitution, those went smoothly. And the categorical operations on syntax and the lemmas about, categorical lemmas about the interpretation function, all of those went absolutely as smoothly as we could hope. That was lovely. What's the bad news? So the first problem was that the syntactic category involves quotients. So the first problem was the quotients, and the second problem was the quotients, and the third problem was the quotients. The quotients are just dreadful. They were just horrible. Being slightly more specific, it was the intersection of the fact that we had in the way we were using CWAs, CWFs, you have a dependently typed structure where you have maps between objects in a category. The type of maps is dependent over the type of objects. And the objects were quotiented because in the syntactic one, they're contexts modulo judgmental equality. And then in Unimath's quotients, the dependent eliminator doesn't compute judgmentally. And with the interaction of these two, it ended up worse than setoid hell. So maybe it would have been better to just stay in setoid hell, improve the other things, but maybe we should have just stuck with the setoids. And so the Koch formalization, unfortunately, is, as I mentioned at the beginning, not complete to initiality. What's complete is the part, as it were, that's pre-quotients. which contains the parts a lot of what you want for applications, in particular the interpretation function and its main properties. We've got out of this. That was all part of what went very nicely. So you can find it on GitHub, look at it, look how it works. It's all good. What's incomplete is, and where we really ran into the mud and haven't done much more in the last year on this, year and a half even now, is the post-quotient parts. So the parts which got into given a syntactic category and anything on that involved quotients. And so that's where I'll wrap up for this one, with the frustrating note of the incomplete formalization that ran into the mud, and I'll hand over to Guillaume to tell you about how, in their approach in Agda, it worked more nicely, they didn't have quotient problems, everything went better, and they got a complete formalization of initiality. Thanks very much.
Okay, thank you, Peter. And if you unshare your screen, I can share mine. Okay, so thank you, Peter, for the first half of the talk. So let me now talk about the same thing, but about the initiality proof in Agda. So the formalization in Agda is done mainly with Menno de Bauer, but of course it was together with Peter and Anders. Okay, so some features of what we proved. So we have initiality for Martin-Löf type theory with quite a few type constructors. We have bitypes, sigma types, identity types, natural numbers, binary sums, empty type, unit, and an infinite hierarchy of universes, which is stable under all the previously mentioned type formers. So it's a fairly complete version of Martin-Löf type theory. So the syntax is exactly like Peter described. So it's fully annotated, well scoped, but row syntax. And we have Tarski style universes. And finally, substitution is like a meta operation defined on the syntax. It's not integrated in the syntax. So where we differ on the formalization with what Peter presented is the models. We're not using category with families, we're using contextual categories together with some extra structure for the type formers and term formers and so on. So I will present what that means. And finally, this is all formalized in Agda. And also the meta theory we're using is Agda together with the type prop that we'll talk about in the next slide, together with a few axioms, namely function extensionality, propositional extensionality, and quotients. But we are not working inside of homotopy type theory. We're just working in regular Agda with this type prop. Okay, so what is prop? So prop in Agda is it's not the same thing as prop in Coq. It's not impredicative. It's a type of strict propositions. So if you're using Coq, it's available under the name S-prop. The idea of a strict proposition is if you have a strict proposition A and two proofs of A, U and V, then U and V are judgmentally equal. So that's very convenient because then we don't have to worry about like equality between proofs and stuff like that. And we use that quite a lot. In particular, our identity type is prop valued. So we have like UIP judgmentally, basically. We use a notion of partial element. I will talk a bit more about that later, but basically if you have a type A partial element of A is just a proposition that tells you whether it is an element or not, and then the function from that proposition to A. So if P is the false proposition, then it's an undefined element. If P is true, the function will give you which element it is. And because two elements of P are always judgmentally equal, this function F picks out at most one element of A. Then we use equivalence relations, which are just prop valued relations, reflexive, symmetric, transitive, and so on. And there are several inductive families which are in prop. For instance, derivability of judgment, we define it as an inductive family in prop. In particular, that means we never talk about derivations themselves. We just talk about derivability of judgment. So there are some restrictions on prop. In particular, if you have an inductive type in prop, you cannot eliminate that to a set. You can only eliminate it to a different prop. And for some cases, it can be an issue, but for this project, it has basically not been an issue, because every time we want to eliminate from prop, we always eliminate into other props. So that worked pretty well. Okay, so now let me introduce our notion of models for the type theory. And let's first start by a very quick review of like essentially algebraic theories, because the model will be based on essentially algebraic theory. So there are various ways to define essentially algebraic theories, but I like this very syntactic way. So an essentially algebraic theory consists of a collection of sorts. So sorts are not dependent, but you can have many of them. Then you have a collection of function symbols that takes a certain number of arguments in certain sorts, certain equations, and it returns something in a different sort. So the idea is that those will be partial functions defined only when the equations hold. And then a collection of equations that are supposed to hold for the general thing. So if you have an essentially algebraic theory, it automatically gets a category of models. So a model of this essentially algebraic theory is just for each sort you give a set. For each function symbol you give a partial function that goes from the right set to the right set, and that is partially in the correct way. And you want it to satisfy all the equation that you gave. And you also automatically get a notion of morphisms between two models simply by saying a morphism. It maps the sets to the corresponding set for each sort, and it commutes with all the partial functions. So the reason I'm talking about that is because contextual categories with structure will be a special case, will be an instance of an essentially algebraic theory, and therefore will automatically get the category of all such models. Okay, so here is a simple example of essentially algebraic theory. How do you define categories? So the essentially algebraic theory of categories consists of two sorts: objects and morphisms. So morphism is like all morphisms put together. It's not dependent on the domain and the codomain, as you may see in type theory. It's like all morphisms. Then we have four functions: domain, codomain, identity function, and composition. So not that composition is a partial function, because you want the domain of F to be equal to the codomain of G or the inverse. And a bunch of equations. For instance, the domain of the identity function on X should be equal to X, and so on and so on. Okay, so that's a very simple example of essentially algebraic theory. So before I go to contextual categories, let me first explain a bit the idea of contextual categories, how you use contextual categories to model type theory. So given a type theory, we can define a category where the objects are the derivable context quotiented by judgmental equality, and the morphisms are the derivable context morphisms quotiented by judgmental equality. So this is the same thing as the category in that Peter presented. For category with families, you also have this category of context. The difference here is that we don't want to add an additional types presheaf and terms presheaf, because we just want to use this category and that will be enough. The way it works is as follows. So first, the objects are actually graded by the length. So each object has a certain length, because objects are just context. And there is a further operation that takes a context and removes the last type. And well, there is a lot of operations for stuff in the type theory. But then if you want to talk about a type, a type A in context gamma, you can actually just do the context extension gamma A, and you get another object. So anytime you want to talk about, let's take a type in context gamma, you can just say, let's take an object whose father is gamma, and that's equivalent to saying, let's take a type over gamma. Similarly for terms, if you have a term U of type A in context gamma, you can see it as a context morphism from gamma to gamma A, which is just the identity on gamma and the term U on A. And so this context morphism has the property that if you compose it with the projection back to gamma, you get the identity. And therefore, anytime you want to talk about a term U of type A in context gamma, you just say, let's take an arbitrary morphism from gamma to gamma A, such that when you compose with the projection back to gamma, you get the identity. And that's equivalent to saying, let's take a term. Okay, so we'll use that in a few slides, but first, let's look at the essentially algebraic theory for contextual categories. So the main difference with category one difference is this grading by length. So a way it's typically presented is that you have a function from objects to natural numbers, but for various reasons, it's not a very good way to work with. So instead, what we do is simply we increase the number of sorts. So now instead of having just sorts for objects and for morphisms, we have for every natural number n, we have a sort of objects of length n. And for every natural numbers n and m, we have a sort of morphisms such that the length of the domain is n and the length of the codomain is m. So we still have all the operations for categories adapted for those new sorts, and then a bunch of new operations. So this FT is this further operation that I mentioned. The idea is that it takes a context and removes the last variable. PP will be the projection from a context to its father. Then star is doing substitution on types. QQ is something about picking the last variable of a context. SS is picking the last term of a context morphism. And then those two things are about the empty context. And there are a bunch of equations governing how all the things work together. Okay, but so once we have that, we have a notion of contextual categories, but for now there are no extra structure. There is no extra structure. It's only the basic thing on which we can now add type formers and term formers. So the idea will be that for every new type former or term former that we want to add to a type theory, we add a new operation corresponding to it on contextual categories. So let's take formation of pi types. So this is the typing rule. You have a context gamma, you have A, a type in gamma, you have B, a type over A, and you get a pi type over gamma. So the way it's expressed is this way. So given gamma, so gamma is supposed to be a context, so now it becomes an object. Now A is a type over gamma. So we saw earlier that types over gamma are simply objects whose father is gamma. So those two arguments give you that A is a type over gamma. Same for B. B is an object of length 1 more whose father is A. So that expresses the fact that B is a type over A. And then if you have all of that, you get an object, which is this pi. But this pi type should be should correspond to a type over gamma, which means that it's not only an object, it's an object whose father is gamma. And so we then have a second constructor or second equation in our essentially algebraic theory, which simply says the father of the thing we constructed before, or the thing we assume the existence of before, should be gamma. So for terms, it's essentially the same thing. It's slightly more complicated, but if we look at the successor function, so gamma is a context, U is a term of type n, therefore successor of U is a term of type n. So now we say, assuming we have a context gamma, then we want to say, assuming we have a term U of type n, and so to remind from a previous slide, a term U of type N is just a morphism such that when you compose with the projection back to gamma, you get the identity. So this is what this is term U is doing. So is term U is just an equation saying compose U with the projection and you get the identity. So take an arbitrary morphism such that when you compose it with the projection, you get the identity, and such that the codomain of U is the natural number structure on gamma. So that says U is of type NAT. And because the conclusion has to be that successor of U is a natural number, we have the same structure in the sense that this first constructor gives you a morphism, and then you have one condition that tells you this morphism has to be a term, and then a third one that tells you this construction has to have as codomain the natural numbers on gamma. And so for every term former and type former that you have in your type theory, you do that. You add those conditions. So you have those new structures to the essentially algebraic theory and those new equations. So for those, for pi formation and successor, it's relatively easy. For other things like, say, the J elimination rule, it's much more complicated because there are substitutions going on and stuff like that, but it's essentially the same idea. Okay, so that's not all, because we need more structure, so we need some naturality conditions. So naturality corresponds to the fact that substitution commutes with term and type formers. In a sense, if you do a substitution of delta in a pi type, then it goes into the A and into the B, except that the substitution into B is kind of a little bit different to take into account the new variable. But that's just an equation that you can write if you do star. So star corresponds to the pullback or substitution semantically. So if you do star of delta on some pi structure, it's just the pi structure of doing star or star plus on the arguments, and same for terms and so on. So again, there are things to define, the star plus, the star TM, there are things we have to define in addition, but it's doable. Okay, so for every term and type former, we add this equation in addition. And finally, our type theory has judgmental equality rules, for instance, beta reduction and eta conversion. And so we just add the appropriate equalities corresponding to that. So summarizing the last few slides, we now have an essentially algebraic theory, which whose models corresponds to models of our type theory. So it's like contextual categories with a bunch of operations corresponding to all type formers and term formers and the appropriate equalities. So we have one category of models, which is the one we want to prove initiality for. Okay, so let's talk a bit now about the term model and quotients. So for quotients, we use quotients, basically the higher inductive type version of quotients, except that we're using prop. But so given the type A and the prop valued equivalence relation on A, we postulate the quotient with two constructors. We can project from A to the quotient. And if A is related to B by the equivalence relation, then the projections are equal. And this has a dependent elimination rule and crucially a judgmental reduction rule, which makes everything work quite nicely. So one property of quotients we need is something called effectiveness of quotients, which is basically the opposite of this EQ, which says that if you have two elements of A which are projected to two equal elements in the quotient, then A and B are related in the original relation. So that's what I just said. And the proof is quite interesting. So it's basically an encode-decode proof. And okay, maybe I won't go through all the details, but the thing to note is that this proof requires propositional extensionality, because we generalize that by constructing constructing a function to prop, but then we have to prove an equality between two propositions, and for that we need propositional extensionality. And then path induction, and we apply it to the special case. If you have seen an encode-decode proof, you can easily recover it. But this is the point where we need propositional extensionality. And then we can define the term model. So the definition itself is like you just take context and context morphisms, you quotient by judgmental equality, and you prove that it has all the appropriate structure. It's very tedious because it's very long, but it's essentially straightforward. So I just want to show that we actually need effectiveness of quotients with some examples. So for instance, if we want to define composition of morphisms in the term model. So assume we have two morphisms that are composable. So the codomain of one is equal to the domain of the other one. So morphisms in the term model are equivalence classes of context morphism. So equivalence classes of syntax. So we can take two representatives of D and T. So we take two actual context morphisms. Let's call them delta and theta. But for now, we don't know that the codomain of delta and the domain of theta actually match. We only know that if we project to the quotient, we get equal things. That's what our equation here gives us. But using effectiveness of quotient, we obtain that if the projection of delta and delta prime are equal, that means delta and delta prime were related by the equivalence relation, which means they are judgmentally equal. And now that they are judgmentally equal, we can compose the context morphisms syntactically, and we can prove that this is well typed and project it back to the quotient to get the composition of the morphisms in the term model. And so this kind of pattern appears for essentially all operations of the term model, because we have a bunch of equalities as assumptions, and we need to use effectiveness of quotients for all of them in order to get something that we can use in the syntax. Okay, so now we have the term model. Let's talk a bit. So here it will go quite similarly to what Peter said, with a few changes. So the partial interpretation function. So first, the notion of partial function we're using is using this partiality monad. So a partial element of X, as I mentioned at the beginning, is just a proposition together with a map from that proposition to X. And then partial functions from A to B are just functions from A to partial elements of B. Therefore, we can define the partial interpretation function by structural induction on A and U, and it gives you a partial object or partial morphism. So here, one difference with what Peter presented is that we don't actually need an environment. And the reason for that is because we are working with contextual categories, and contextual categories are much stricter in a way that the objects correspond to context, and so they are already ordered in a way that if you just have a dobrain index and an object, you can extract exactly which variable it corresponds to. Something that you cannot do in category with families.
Sorry, Andy Pitts, I think, raised his hand to ask a question, maybe?
Yeah, so the predicativity here, presumably you raise the universe level when you go from B to partial B, right?
Yes.
But I guess that's not a problem.
Yeah, that's not a problem. I mean, we're working in Agda, which is predicative, and we didn't have any issue with that. So, yeah. Okay, so we define the partial interpretation function by structural induction. And so one thing which is nice is that this partial X is a monad. And so in Agda, we can use monadic notation. So here is some example. How do you interpret pi AB? Well, you do the following things. First, you try to interpret A, so in context X, it may fail. If it fails, then the whole thing fails. But if it succeeds, you get this bracket A as a result. Then you need to make sure that bracket A is something over X. So you just assume this is true. So this assume simply means if it's false, then fail. If it's true, then it's true. Good. Keep track of it by this witness. So if we went there, then it worked. Then we interpret B in the interpretation of A that is now available. And same, we assume that the father of B, of the interpretation of B, is the interpretation of A. And then we just return whatever the pi structure in C and with all the things that we constructed here. And exactly the same for successor function, and we assume that it is a term and that it has the right endpoint. So that's pretty nice and pretty readable. So then we have the totality theorem, just like Peter mentioned. So if a judgment is derivable, then the interpretation of that thing is defined. So for context, for types, for terms, for context morphisms, and then for equalities as well. So if some judgmental equality is derivable, then the interpretation of the things are equal in the syntax. So here we do use equality of objects, unlike in Peter and Anders' formalization, but that's just because contextual categories are naturally suited to use equality of objects, and categories with families are not. Okay, and then that's also something Peter mentioned, that interpretation commutes with substitution. So if you interpret a syntactic substitution, you should get the semantic substitution of the interpretation of the type and the morphism. So I won't spend too much time here. And then I'll spend a little more time, but not too much, on the proof of initiality. So there are two parts in initiality: existence and uniqueness. So for existence, we want to construct a map from the term model to an arbitrary contextual category. So this is relatively easy. You just use the partial interpretation function. You use the fact that it's actually total on derivable context or context morphisms, and that it respects judgmental equality, and therefore it goes through the quotient. And all the structure, it just follows from the syntactic counterpart of that structure. So that's, again, somewhat tedious to do, but relatively straightforward. And then uniqueness. So this one, so maybe some of you have heard the talk where I was talking about that, and where some inductions were not structural. So now this is fixed. All inductions are now structural. So the first lemma is that we are given two morphisms now from the term model to an arbitrary contextual category C, and we want to prove that they are equal. So the first lemma will prove is uniqueness for types. So this basically says that uniqueness is preserved by context extension. I guess we can say it this way. So if f of gamma is equal to g of gamma, then f of gamma comma a is equal to g of gamma comma a. And so this lemma is proved by structural induction on A. For instance, if A is a pi type, then f of gamma pi AB, so this gamma pi AB is just a pi structure of some contexts. Now f commutes with pi structures because f is a morphism. So we get this thing. And now we know that f gamma is equal to g gamma by assumption. F gamma A is equal to g gamma A by the induction hypothesis for A. And f gamma AB is equal to g gamma AB by the induction hypothesis for B. And then we can just commute things the other way and we get the lemma. Then we have a similar lemma for terms. If f of gamma equals g of gamma, then f of the thing corresponding to term u is equal to g of the thing corresponding to term u, and same proof by structural induction on u. And therefore we get uniqueness of the map. We get equality between f and g. So for any context gamma, we get f of gamma equals g of gamma. So that's like direct from the lemma on the previous slide, uniqueness for types. And for context morphisms, it's slightly less obvious because we only prove them here for a special kind of context morphism. If you have a general context morphism delta u, you first split the delta and the u, and then go through it and then apply the uniqueness for term and put it back together. Okay, so that's the end of the proof of initiality for this type theory. And so the last few words on maybe some future directions. So in the formalization, there are still some performance issues. In particular, it takes a lot of memory and a lot of time to type check. And we're not entirely sure how to fix that, but this is something that should be fixed. So for now, it needs like something like 25 gigabytes of memory to type check, which is not optimal, of course. Then maybe we should add even more type formers. For instance, one non-trivial that we haven't done is W types, but well, that's future work. And then finally, as Peter mentioned, we should use this experience of working of proving initiality to prove it for an arbitrary type theory, where of course the main issue here is to actually have a notion of arbitrary type theory and then manage to prove initiality for that. Okay, so thank you everyone for listening, and we open for questions, I guess.
Wait, so before we open for questions, I'm going to say thank you very much, and please join me in applauding. Don't unmute your microphone, so you should only hear me and no one else. Okay. Okay, well, thanks guys, that was great. So here is what we're gonna do. We're gonna take a bit more time if we need to, and we invite everyone to make their statements about initiality, about the proof, ask subsequent questions. Some people couldn't help themselves and made comments in the chat. Now would be the time to make these comments loud so that they can be recorded for the future generations. And as soon as I said that, Thorsten raised his hand, which comes as no surprise to anyone, I think, at this point. So I'm gonna let Thorsten ask the question.
Yeah, I'm sorry for abusing the chat. It's I don't know if my hands do this. I try to stop them, but it's like Dr. Seltsam, you know. It's really difficult. Yeah, I'm a bit shocked. I feel a bit like a broken record, you know. I try to explain my concerns about this project. And now I would expect that Peter gives a talk. I mean, he's a very clever guy. That one of the first things he do is to refute me and show that this is complete whatever. But he's not doing it. So I was waiting for the point. Yeah. So let me make my point. Okay. So first of all, we have higher inductive types and higher inductive and quotient inductive types, and all I need to do is take the description of these algebras of categories with families and write them down as the constructors for a quit, and I have solved the initiality problem. And I don't understand why I shouldn't do this. Maybe it's too easy. I don't know. I mean, there were he made some remarks about essentially algebraic theories, which why? I mean, essentially algebraic theories are a way to scare your kids, you know, because they're equivalent to generalized algebraics, but they're understandable. Whether those I can't read. I mean, it's and I'm sorry, yeah. So generalized algebraic theory, RK, quotient inductive types. So use them, and what got lost? We cannot. What have some meta theorems which are not whatever formalizable? What are they? I wasn't told. And we can prove, actually, we can prove normalization and decidability. So okay, there's still. I need to kill you completely. Okay, then there is still a gap between the syntax, maybe in characters or bits, and what you write down, and that should be done but not by somebody as clever as you two. I'm sorry, it's a waste of human intelligence. Yeah, but okay.
Okay,
yeah.
first of all, before Peter replies, I would like to say that Hottest does not endorse murder in terms of killing someone completely. This is not the official party line here. Thank you. And now I'll hand it over to Peter.
So also before I answer, I want to give a meta answer, which is that each time I give one of these talks, as you said, you ask this question and you can sort of briefly outline your position on this, and then I briefly answer giving my position on this, and then we have to keep it very compressed because we want to get onto other questions. And so we never properly have time to resolve it. So I'm not saying let's do it now, but what I will say is email me, it'll be nice to get a good proper discussion in on this. And if we were at a physical conference, I'd say let's go out to dinner, but let's do it properly by email and get into it so that we don't have this quick superficial version of it every time. Maybe
Twitter, that's a good place.
And that's also to anyone else who has similar kind of feelings. I'd rather kind of go to dinner and chew through it properly. It's interesting, they're good questions, but having a brief version of them for the fifth time, I don't think we get any further with it. But I'll give that brief answer for everyone else's sake, if it not really for Thorsten's, which is that I didn't mention it because I think it's a lot like the in the slide where I mentioned essentially algebraic theories and logical framework embeddings as two of the other syntaxes that some people prefer. There are things which I think those syntaxes are good. I'm not saying get away with your quotient inductive types, they're stupid. I'm saying I think those are good, those do some things very cleanly, but also there are some things that the traditional presentation of syntax achieves and some kind of things you can do usefully with it that I don't know how to do with the other syntaxes, except for the logical framework for some of those things, thanks to Umura. So I think that those syntaxes have value for some purposes, but this has value for others. It's a bit like the kind of old joke about you solve the homotopy hypothesis by saying a space is a Kahn complex, an infinity groupoid is a Kahn complex, therefore spaces are infinity groupoids. It both solves it in a meaning, and it's a good point as a joke solution, but at the same time you also still care about the other forms of the theorem that are non-trivial. So that's I think my short answer. And then I know it's not a fully satisfactory answer, but that the fully satisfactory version, Torsten and I should get into it in depth together.
We can have a subsequent special event that will arrange that. I believe it won't be just Torsten though, that you'll have to go up again. But okay, maybe let's move on to the next questions. And first, if there's time, we'll have maybe a rebuttal from Thorsten later. But I think Mike Schulman is next.
Thanks. So I have a mathematical question on one of your last slides, Peter. When you were talking about the problem being quotients, you mentioned that there were two pieces that went into that. And so that being a problem. The first one was that the morphisms are dependent on the objects, and the objects are a quotient, and then the quotients in Unimath don't compute, their eliminator doesn't compute. So I was wondering what you think about the prospects for solving those problems, both of them, or just one of them, by using a different design or a different system, right? For instance, in Agda, they have these quotients that I guess presumably compute better. In the Hotcock library, we also have higher inductive quotients that compute. Or on the other hand, I could imagine maybe if you care only about maybe a weak initiality instead of a strict one, maybe you could avoid having to quotient the contexts at all.
So, right. Right, so yes, several different sort of option solution questions there.
Peter, can you put your slides on?
Yes.
Maybe just so that we have, thank you. Yeah.
And
then
let's see, where have they gone? I have them somewhere around. Have I done with the slides? I'm sure I had them some. sorry, lost my slides. All right. I instead of screen sharing, because that gets annoying a bit for people, I will I'll share the slides in the chat so that anyone can look through them at leisure. Or no, file sharing is not allowed in chat. I guess file sharing is disabled in chat.
Post a link. Are they up somewhere?
No. No. Chris, are you able to?
I think sharing them would be a good idea. I mean, screen sharing.
All right. Yes, I will screen share them now if I can't share them in chat.
I don't see this option on my control. I know, but I think screen sharing is better, so that we all know what we're looking at.
What Mike was asking about was where I've saying that it's the interaction of having a dependent type dependent over quotients and unimass quotients, the computation issue. So a system where quotients really computed absolutely as nicely and as well as you want, this might be nicer, I'm not sure, because I've never used such a system. The quotients in HOT, I haven't tried them for about a year, so if they've been improved by it since then, they may have been improved to be closer to this. When I was last trying to work out if they might help this, I did a quick testing a few things with them and didn't feel convinced enough to try porting the development over to those. And so in Agda with the strict quotients, there and on the one hand, that would sort of, Guillaume's already done that. On the other hand, there is some sort of foundational trade-off in what kind of equality you've got and what identity types you have. That what you can get out of it is closer to having done it in extensional type theory with UIP than doing it with intentional type theory, because you defined your contextual categories in a way that assumes that the essential algebraic conditions use a strict equality. And so you can't get examples based on types that don't have something pretty close to a strict equality. So you lose examples where the type of objects didn't have UIP, so you lose a lot of examples. Having a version which avoids quotienting contexts, yes, that I think is the nicest solution. The one next time I try implementing something like this again is the one that I'd like to try. That, unfortunately, as far as I can see, you can't do it while remaining within the conventional definition of categories with families, because, or at least not in any version where you have a context extension operation, because the context, you have to quotient your types in order for the equalities to hold, but your context extension operation has to take types into contexts. So then if the types are quotiented, then the contexts have to be quotiented too. And so the ways that I know to do that are either going to essentially either going to a two-category based or a setoid based view, which are pretty close to being the same thing of a definition of categories with families. And so, or categories with attributes or whatever. So, right. So the thing I think I would next have a go at would be having a go at that, using a setoid-based or two-categorical version of categories with families, and avoiding quotienting the objects and hoping that that would work better and give something that would compute nicely. So yes, of the options I've thought carefully about, that's a rough rundown of them.
Mike, any?
That's great, thanks.
Okay, then we're gonna move to Carlo. Carlo's next.
Yep. Mm-hmm. Okay, so first of all, my question doesn't contain the words GAT or LF or QUIT. Just as a disclaimer. So first of all, thanks for your early slide with the objections. Oh, your slides have just disappeared. But
how about we leave them on for?
Sorry, I wasn't
for the remainder of the session.
If a question is about something on one of my slides, it makes sense to have them up. but it might also be about
It is.
slides or not at all. So
Yeah.
How about we leave them, and then if it isn't, we'll change it.
Well,
We don't need
anyway,
to go into the hardest possible solution.
Right. So maybe if you go to your slide like 5 or whatever it was, the objection slide. Right. So yeah. So I was saying thanks for this slide, because I think that, I mean, one thing we can all agree on is that that, you know, changing the syntax or changing the semantics greatly changes first the difficulty of the theorem, as well as the usefulness of the theorem. And I think you would agree with that. But that's, and I think that a lot of the kind of debates that all of us are having have to do with, you know, having different choices or wanting to use different things, you know, for each of these input output. And I mean, it's worth debating what they should be, but I think it's really important to just note that that might be at the center of a lot of the confusion. But then, so given that, I was going to ask, in basically, why is this the right kind of syntax to be or interested in, or maybe why is this the right kind of presentation of type theory to be interested in? And what I mean by that is, you know, so you're talking about this sort of, you know, inference rule kind of presentation, right? That I like to call it jokingly a calculus of fractions, you know, but no one really uses that. And I kind of feel like part of where we went wrong is that we started off by insisting that that was what type theory is, and that kind of put us all on the wrong foot. Like, for example, you know, you're talking about admissibility of substitution, but if you actually look at like what's going on in a proof assistant, that's not really, I mean, that doesn't really come up. What you actually need is something kind of more interesting, and which does rely on normalization. So I'm not criticizing you for not proving this. I'm just, you know, suggesting, like, for example, you want to know, you know, admissibility of first, right? Because like all of the elimination forms are not actually like constructors. They're defined, you know, by cases where on a pair first actually does something, but on you know, on a neutral, it, you know, it is a constructor and things like that. So I guess my question, sorry, I wasn't trying to go on like a comment, not a question, but I guess that's what happened. So my comment question is, you know, do you agree or disagree with that? And like, do you think that, do you have reasons why you think this calculus of fractions is the right thing to be studying?
right, okay, so I guess the first bit of an answer is that I don't think there's any one thing that's the right thing to be studying. That ideally have sort of the theory we have would encompass all of these and put the connections sort of in between them. Just as on the semantics side, also there's lots of good notions of models. You can have a model that's sort of like a category of attributes or a contextual category, or you can have, and you can have something like, you can look at infinity toposes, or you can look at model categories of the appropriate structure, or elementary toposes, or whatever. There's lots of things on both the syntactic and semantic sides. Mm-hmm. But there is, in a way, there's kind of the places where the two of those approach each other closer than other places. And initiality feels like it should happen at one of the places where they approach each other most closely, having a syntax that's sort of got the cleanest structure to be close to the semantics, and a semantics that's sort of most closely mirrors some kind of syntax. That it would be bizarre to go directly from sort of streams of ASCII to infinity toposes. That's not where you prove your initiality theorem. You kind of pass your streams of ASCII into something that, what I would suggest, right, and so and then also you get your infinity toposes via the categories of attributes or whatever. And to me, the places where, on the syntactic side, the syntaxes which most closely seem to approach the categorical analysis are the logical framework embedding and the non-embedded, and what I've been calling the naive, what one might call the traditional notion of syntax with binders. That they're they've got the kind of least elaboration or sort of syntactic sugar involved. They've got everything fully annotated, fully elaborated, fully parsed. The logical framework and the non-logical framework embedded syntax are the two that come closest to it. So if you're comparing it with something like like what's actually used in implementations, the various versions there, those I feel are where you haven't yet come as close to the syntax, the semantics as you to be ready to prove initiality. Elaborating or getting those into initiality is most easily done by translating them into either the logical framework syntax or the naive syntax or something in that sort of space. And then the reason why I think it's, one of the reasons why I think it's, to me at least, the naive syntax seems slightly conceptually, at least conceptually prior to the logical framework one, is that most presentations of a logical framework come down to first having a specific thing presented by a calculus of fractions into which the other theory is then embedded. So kind of it all, sooner or later, comes down, comes down to this. Jacques Correct, by the way, asks in chat, it sounds like I'm reinventing compiler architecture. I'm not trying to reinvent it, I'm trying to describe it as it applies to this. I'm not saying I invented this view, I'm then saying here's how this viewpoint, which comes from there, explains, I think, why I see this as either this or the logical framework as the places it's natural to try and prove initiality. So, so I think, does that kind of answer Carlo's question?
I mean, I guess then my, right, so I definitely agree that, you know, you want to pick carefully like the start and finish. I guess my main like critique would just be that I don't feel like the place you've chosen to start, like that's actually something anyone uses for anything. So then it's, you know, therefore, okay, you've kind of chosen it to kind of match up with a certain semantics, but like no one's actually using this input, so like why
I know, I'm not saying I agree it's not what one uses in an implementation, but it's not so much, I'm choosing it as the point where whatever point you start with, kind of, you want to go on the long journey from something which you might use in an implementation to an infinity topos or something like that. Mm-hmm. And you do some of that journey on the syntactic side and some on the semantic side, and it's somewhere you pass from one to the other. It's that if you try and go directly from the one you would use in an implementation to the semantic side, it will just sort of be doing 10 things at once and be incomprehensible and a vast amount of work. It's much cleaner to factor it somehow. And so I'm not choosing this as, I'm claiming it's a starting point that someone comes from. I'm claiming it's one of the points that I think makes a good factoring point for it.
Okay, well, yeah, I think there's a lot more to discuss, but I take your point. We can maybe discuss it on the Torsten forum or something like that. Thanks.
Okay. I believe I didn't imagine it, but I think I saw Andy Pitt's hand up for a second, but I think it's gone. I don't know, Andy, if you're still around. And
yeah, sorry, I lost the will to live. I put my hand
down. Okay. Okay. So this is like permanent. Again, Hottest does not endorse depression, I guess.
I have a couple of questions, if I can jump in.
Yeah, go for it.
So the first one could be answered by either Guillaume or Peter. It's how hits might fit into this story. So you've almost got book hot, but you're currently missing hits. And I'm just curious whether you think that would be very hard to add on or relatively straightforward. Either one of you could answer that.
Yes, so if you just want hits in the hot book version, then it should just be straightforward. I mean, it shouldn't be any different than adding natural numbers or anything else. Then of course there is a question of what do you want to be a definitional reduction rule, what do you want to be propositional, but that's not really a problem for initiality. You can put anything definitional or propositional, it won't really matter for initiality. It will matter a lot for which models you want to have, but initiality should work without issues for anything you choose. So that's part of the robustness that Peter was mentioned. Like any version of high inductive type is reasonable, whether or not it has actual models. So yeah, there shouldn't be any issues.
Peter, do you want to say anything about the semantic side of that?
Yes, so right, so again, roughly echoing what Guillaume says, that the approaches to hits that essentially are within Buckhart that don't change the judgment forms of the theory, all of those should fit very happily into the robust extensibility of this, that it should be straightforward to add them to the syntax in either of these formalizations, add the definition of the corresponding structure and the semantics, and then extend the proof to that. And it should be just sort of one more line of definition, one more constructor in the inductive type on the syntactic side, one more definition of in the logical structure on the semantic side, and then one more case in every induction for each new rule that you want to add. So yes, anything that doesn't change the judgment forms or the structural rules and is reasonable in a sort of heuristic sense that is complicated, slightly harder than one wants to define, anything like that, both these formalizations are fairly carefully designed so that they should be able to extend to straightforwardly. On the other hand, things like the nice computational higher inductive types of cubical theory rely on having the judgment forms and the structure of the theory a bit more substantially changed. So those would those wouldn't fit into this.
Great, thanks. And if I can also just ask Guillaume another question. So Guillaume, you didn't mention that in order to process your file, you needed to assume an inconsistent hack to get the memory usage down. And that without that hack, I tested and 195 gigabytes of RAM isn't enough to process even the first of your files. So
the first file doesn't use it.
Or sorry, so I guess it's maybe the second. It's the second one, maybe. Term model id or something like that.
Oh yeah, right. So indeed, so there is still some hack that is used to like remove some stuff, kind of remove some stuff in memory or something like that to make it to make it actually type check in a reasonable amount of time and amount of memory. So that's also something that we would like to get rid of, and that's also something we don't really know what's going on, but I mean we have been making some progress. It's now much less needed than it was before, but yeah, so it's used in a very safe way, in a way.
I agree.
Yeah. So we're not really concerned about that it would be inconsistent. But yeah, that's definitely something that is still unsatisfactory in the Agda formalization, and that we don't really know yet how to fix. But
great. Okay, thanks. I just wanted to make sure that was mentioned.
Yeah, thank you.
All right. Well, with Peter going 10 minutes over time, we still have 2 minutes for questions if we want to exhaust the full 30 minutes of questions, comments, and as maybe we saw, especially in the beginning, insults.
I can ask a question.
Go for it.
Right. So I was wondering what's kind of wrong with the argument of using initiality for generalized algebraic theories and then lifting that to the contextual side to get initiality there. Why doesn't that give us what we want?
It gives us initiality for a slightly different syntax from what we proved it for here. And for a syntax, so I mean, it gives us a version of initiality, but it gives us initiality with respect to a slightly different syntax that isn't structured in quite the same way. And having the syntax given in this way, because of the way it's structured, it's a syntax which has advantages for other purposes, for various purposes. And so initiality for generalized algebraic theories, it's a different theorem. It gives us a different form of initiality, which is useful for some things, but different things.
Right. I think we have one more question, one more hand raised. So wait, don't. I don't know what these Swedish things are, but yeah, don't do anything to the slide. So there's one more hand, Jesper.
Yeah. Hello. Can you hear me?
Yeah, we can hear you.
Okay, thanks. Yeah, I was wondering. I mean, it's a nice result. Although I would still be interested also in the answer to Thorsten's questions. But I had another question also, which is like, where do you plan to go on from here? Like, do you still want to go to proving the full statement? Or do you see any applications now that this is formalized? Like you mentioned some applications in the beginning. Is this something we can now actually build up on further on the Agda formalization or the COC one?
Yes. Guillaume, do you want to take that first, or shall I? I think it was to us both.
Yeah, so I guess the main issue with the Agda formalization is still that it requires a lot of memory and a lot of time to type check. So if you don't have 25 gigabytes of memory, it might be difficult to actually build upon it. So I guess that's the main issue. Then there are a few things that should be streamlined to make it even easier to add new things. But at least if you have enough memory, it is possible to just try to add new typeformers.
Okay, but that's like adding new typeformers. That's
yeah.
I guess it's very interesting. But also like, can you like use this to give different interpretations of the syntax that would not be, maybe wouldn't be expected that you could do this, or like use this in other ways? I'm not sure what exactly I'm looking for, but I'm just wondering.
Right.
Because that's the result in the end, that you get some kind of interpretation in a different category, which is not initial of the syntax, right? So can you apply this somehow?
So if you can define a model, then you can apply the formalization to get a map from the syntax to that model. Because of prop, it might be not that easy to define a model, because you may need to use, I mean, unless you are assuming some kind of strong transport, because the problem of prop is that you can't transport along it. And if you try to define a very basic like set model or type model, you do need some transport along equalities. But apart from that, it should be possible, I guess, but we haven't tried to do anything in this direction. And so at least I haven't really thought about which kind of other applications like that. Maybe Peter has an answer.
Yes, so that direction of application is actually one of the things that I kind of been very hopeful for getting out of this, and is one of the reasons that in the COC version of the formalization, we preferred to avoid having something like strict prop, because that makes it harder to get examples unless one assumes UIP. And if one assumes UIP, one can get examples and combine that with the strict prop. But without that, it's, I think, a bit harder to get examples using that. So, so I'd been hopeful of this approach if the quotients hadn't sort of got bogged down so much, giving something where a lot of the nice proofs that are done using say both mathematical models and some syntactic translations as well that can be given quite cleanly by putting the target into a category of attributes sort of package. Right, I mean, I'm hopeful to get out something that would compute, where you could take your syntactic translation, put the target into a category with attributes, and actually run the interpretation function and see if it worked. run the totality proof, see if it gave you a thing there. And that's where, unfortunately, this version seems to have not come out, because really of the, I think, coming from the use of quotients, it doesn't quite feel like it's going to give something that will compute nicely. I'm hopeful that if this was switched over to trying to do it with setoids again, one would actually get something that computes a bit more nicely. As ever, one of the things about setoids is reasoning about them in certain ways gives setoid hell, but the whole point of them originally, or one of the points of them originally, is that they're explaining what goes on with computation. You compute with representatives and you don't quotient. You keep the representatives that are what a computation works on. So especially if we reported this over to be setoid-based again and could do that without setoid hell getting too bad, I would be very hopeful that applications could be very much done where motivating models, both sort of set or whatever kind of mathematical style models one has, and also more syntactic translation results, that one could really get those computing with this. There's no obstacle to that in principle. In principle, it should work. It should give something that computes.
Okay, cool. Yeah, thanks for the answer.
All right, we should be wrapping up. I saw again for a second Andy Tietz raised his hand, and I hope he rediscovered the will to live. But maybe it was that Thorsten trying to killed the wrong person. So if there's one lesson from this talk, other than the initiality being proven, is Thorsten, you need more firearms training. But yeah, anyway, Andy, if you want to ask a question, that'd be cool. And
no,
yes,
thanks. No thanks. It's time for dinner.
Time for dinner. Okay, well, it's time for dinner. So before dinner, let's thank Guillaume and Peter again. So thanks, guys, for the talk and for answering all the questions, as provocative as they may have been. Okay, and so that's it for today. I think